All right, we are going to revisit this example, namely q adjoint I root 2 is this set that we started with at the very beginning of the chapter. We're going to show that this set theoretic description is correct. Namely, we know the left-hand side is a field. It's the intersection of all fields containing q, I, and root 2, or equivalently, it is the smallest field containing q, I, and root 2. The right-hand side was our guess as to what that was. It is just a guess. Okay, so we need to prove the guess is correct. The first thing we need to do is we need to show, I'm going to call this F. We need to show that F is a field to begin with. Once we know it's a field, the proof that these are equal isn't too difficult. Okay, so let's go ahead and do exactly that. The check that F is a subring is not hard. You use the subring test, and you have to multiply two terms with two expressions that have 4 terms, so 16 products. You sit there and you do it. It works out. Said better, only the multiplication is tedious, but the things you're going to be the terms you're going to be multiplying involve rationals, I, and root 2. All of these guys, when you multiply them, you stay within this collection. So you can't ever leave the collection. So the fact that it's going to be closed under multiplication is just sort of a natural consequence of us adding in all of the possible products. Notice if I didn't put this last part here, it would not be a field. It would not even be a ring because we don't have I times root 2. So it's very important that that last part is there. And then what we need to do, we need to show that F has division. And really this amount, since it's closed under multiplication already, this is the same as having multiplicative inverses. So we're just going to show it has multiplicative inverses. Okay, so the first thing we're going to do this is we show that if p plus qi plus r root 2 plus si root 2 is 0, then it must be that all the coefficients are 0. Now this seems intuitively obvious. It's not. We'll learn how to do this in a better way here in a second. But it's not just like, oh yeah, of course it has to be 0. There is some argument here. What this is saying is that rationally, the number 1, I root 2, and I root 2 are Q linearly independent. So the linear algebra version of this is the collection 1, I root 2, I root 2 is Q linearly independent. Okay? And there will be some vector space language that we'll throw in the next chapters. All right, so this is the first thing that we're going to do, so let's prove it. Let's move all terms with an I to one side. If we do that, on the left, we just have p plus r root 2, and on the right, we're going to have negative I q plus root 2. It's negative because we moved the positive terms over, and I factored out a negative I from both of them. All right, that's fine. The right-hand side is a purely imaginary number, and the left-hand side is purely real. So on the left-hand side, this is purely real. And on the right-hand side, this is purely imaginary. The only time the real and imaginary axes intersect is at 0. So the only purely real and purely imaginary number is 0. So that implies p plus r root 2 is 0. And q plus r root 2 is 0. The real imaginary parts both have to be 0. All right. Root 2 is not rational. So if p plus r root 2 is 0, this tells us that p and r are 0. Otherwise, root 2 would be a rational number. You could express it as a rational. And this guy, oops, q, did I miss my s? Dang, I missed my s. Sorry. Q plus s root 2. This guy will tell us q and s are 0. And that's what we wanted to show. All right. So that's the first step. So if we have a non-zero number that looks like this, it must be that one of the coefficients is non-zero. Great. So let's let alpha, I'm going to use some of the book's notation here, be a non-zero expression in our proposed field. We want to show that alpha inverse, we know that alpha inverse exists as a complex number, but we want to show now that alpha inverse is in F. That's what we're looking to show. All right, so let's write alpha as, we're going to write it as x plus y root 2, where x is p plus qi and y is r plus si. That is, x is going to be the first part of alpha, and then we factor out a root 2 from the last two terms in alpha, and when we factor out that root 2, we're left with y. So it's x plus y root 2. Okay. Notice here that x and y are in q adjoint I, and since at least one of p, q, r, or s is non-zero, our x and y are not both 0. One of them's got to be non-zero because one of the coefficients is non-zero. All right. Now what? We are now going to look at beta, and we're going to set beta to be x minus y root 2, so that alpha beta is x plus y root 2 times a conjugate expression. We saw this a little bit in chapter 1. This is still in our set F, right? Because x and y are there. If I negate y, it's still the right form. So this is x squared minus 2y squared, if you were to multiply that out. So x squared minus 2y squared is in F. And let's notice something about x squared minus 2y squared. There's no longer any root 2's. X and y involve only rational numbers in I. So x squared minus 2y squared is actually in this set q adjoint I that we looked at earlier and we proved really rigorously was the right thing. So x squared minus y squared is some u plus vi for u and v in q. And we could sit here and we could plug in x is p plus qy and y is r plus si, and we could write u and v in terms of pqr, and s, but it's not going to end up being helpful. Okay, then what? Well, then alpha beta times u minus vi is going to be what? Well, it's going to be alpha beta, that's x squared minus 2y squared times u minus vi. But x squared minus 2y squared rather, sorry, 2y squared, is u plus vi times u minus vi. And that's u squared plus v squared. Where again, u and v are not both 0. And so u squared plus v squared is non-zero. Finally, alpha is beta times u minus vi, those are in F, divided by u squared plus v squared, and that's all in F. Sorry, I did that the wrong way. Oops, getting a little bit confused here. Alpha times, sorry, beta u minus vi over u squared plus v squared is equal to 1. And this guy here in the middle, this guy is an f. Because when you take beta, that expression, and you multiply it with a u minus vi, that stays in f, of course, because you're just multiplying with rationals and I. And when you divide by a rational, u squared plus v squared is now purely rational. You land, of course, still in f. So this is alpha inverse. And sure enough, it is in fact in f. All right, so f is a field, and this, as you can tell, was kind of hard. Well, it wasn't hard. It was just tedious. Our strategy was, well, to observe that the subring test should be simple. I leave it to you to check that. And then we needed to show it has division. So first we needed to understand what it means to be a non-zero element of f. That was this part. We will always sort of assume this step, namely when we've written out what we think is the correct combination, that the only way that this expression can be 0 is if all the coefficients are 0. This will normally be assumed. And then we do this trick where we sort of, this is kind of like reducing to the q adjoin root 2 case. It's not quite reducing to that. And we have an understanding of how you try to compute multiplicative inverses there, namely you multiply by a conjugate expression. But when we do that, we don't land in Q because x and y were Gaussian rationals. So these guys are in Q adjoin I. All right, so then we do that step again. We've now reduced to a Q adjoin I step, and we multiply by a conjugate expression. And when we do that, what do we get? Well, we get what we want finally. Finally, we've gotten rid of the root 2, and this part gets rid of the I. Now we're left with just a rational, and we know how to divide by rationals. You put 1 over them. All right, the last thing I'll do is what we set out to do to prove that this field is the same as this field. So we had to show this guy was a field first. All right, let's do that. So now to show, that's the inverse part. Now to show f is q adjoin I and root 2. Well, q is a subset of f, and I and root 2 are in f, so q adjoin I root 2 is a subset of f. That's all you need with this smallest language we're using. The generating set is in f, so the field generated by that generating set is a subset of f. Sorry, that's one of the containments. For the other one, take any p plus qi plus r root 2 plus si root 2 in f. Then individually, p, q, r, s, I, and root 2, those are all in q adjoin I root 2. So any arithmetic combination of them is in that set. In particular, I times root 2 is in that set. So we get that last term. And any way of multiplying them and adding them together stays in that set. So p plus q times I is in that set, plus r times root 2 is in this field, plus s times I root 2 is certainly there, because this guy is a field. So it must be that they're equal. This is the other containment. All right, so that was kind of a longer example. We'll have better ways of proving multiplicative inverses exist later. We're using relationships with quotients of polynomial rings, but for now, this does the job. And we have, in fact, constructed a set theoretic description of q adjoin I root 2. We had to prove it was a field. And then what we needed to do is we needed to show that our set theoretic description was correct.